everybody, and welcome to our webinar. Today we are going to talk about the capabilities of Oxygen Power Advanced feature. It is going to be a lot of know-how and theory that we are going to transfer today. But before we start, I would like to explain some organizational things. Like always, on your right side of the webinar tool, you can see a chat window. This chat is used so that you can ask us questions. Those questions are anonymous and only me and my colleague can see them, nobody else. We will answer those questions at the end of the webinar or during the webinar if it fits perfectly. There are also some handouts available for download during this webinar. So let us not waste any time. Let's start with the webinar today. I'm going to be your moderator. My name is Ivica Baresic and I'm sales and business developer from Austria. And I'm joined by my colleague, Raphael Ludwig. Hello, Raphael.
Hi, how are you doing?
I'm doing fine. How are you?
Perfect so far, thank you.
Do you want to say something about yourself and your position?
Yes, absolutely. Thanks for the introduction, Ivica. My name is Raphael. I'm a product application engineer for Devitron and working in the product management department. And I'm going to host the technical part today of our webinar with the topic of the capabilities of our Oxygen Power Advanced feature.
So perfect. It's a pleasure to have you on the webinar today. And let us not waste any time because it's a lot of theory, it's a lot of know-how that we are going to transfer today. So let us start at the very beginning. Let's have a look at today's agenda.
Absolutely. So as the title already says, we will have a deep technical look inside the capabilities of the Oxygen's Power Advanced feature. The most important features thereby are the harmonics calculations. So we will talk about the different available grouping modes. We will talk about THD, THV, THC, and THC. Talk about the sense behind these abbreviations and how the calculations are done. Afterwards, we will have a look inside the higher frequency grouping and the sense behind that. Then we will also talk about the power harmonics calculations. And last but not least, we will have a technical look into the calculation of the supra harmonics. The second big feature, the second major feature inside the Oxygen Power Advanced feature is the flicker calculation. On the one hand side, the so-called voltage flicker evaluation and calculation according to the IEC 61415 standard, and secondly, the current flicker emission according to the IEC 61400-21. We will have a look inside the calculation and into the channels which are output and automatically determined by Oxygen. Finally, we will quickly have a look inside the so-called rolling computations and the sense behind that. And at the very end, we will have a quick and a short outlook what new features regarding the power calculations will be inside the next Oxygen 5.5 release by the end of March.
Okay, and since I've seen some further people have logged in, just once more the hint, use the chat window on your right side to ask us questions. They are anonymous and we are going to answer them. Please use this opportunity. We are live now. And we are going to be live now as well on Thursday morning at 8 a.m. CET for those colleagues who may be interested as well. And you can give them this news about this webinar as well. Let's not waste any time. Let's talk about harmonics, Raphael, their grouping times and what it is used for.
Yes, so let's start with the harmonics. So after enabling the harmonics calculation in Oxygen, you have the possibility to select between 3 different grouping types. And we will now at the beginning have a look inside the technical differences between those 3 different grouping types. But first, when you enable the harmonics calculation, as I said, you can select the grouping type, and then you have the possibility to specify the maximum harmonic order that shall be calculated. Per default, it is the 50th harmonic order, and you can calculate up to the 1000th harmonics. And when the harmonics calculation is enabled, one harmonics channel for each voltage signal will be added to the channel list here for the first voltage, for the second voltage, and for the third voltage, and also 3 interharmonic channels for the voltage, 1 for each phase here. The same for the current channels, for the current signals. You will have a current harmonic channel for the first phase, for the second phase, and for the third phase here, and as well also some interharmonic channels for all 3 currents of all 3 phases. So when the first grouping type, the so-called grouping mode none, is selected, the harmonics calculation is done in the following way. When we take the spectral analysis, which is the base of the harmonics calculation here, for the harmonics calculation, you only use the bin, the frequency bin, the spectral frequency bin, which is directly placed at the harmonics. So when the fundamental frequency is 50 Hertz, you only use the 50 Hertz bin for the first harmonics, the 100 Hertz bin for the second harmonics, and the 150 Hertz bin for the third harmonic. And all the rest of the spectral information in between these harmonic bins is afterwards summed up and included in the interharmonic signal, like that, how you see it on this illustration here. When you select the grouping mode type 1 instead, the harmonic grouping is done according to the IEC 61000 -4 -7 standard according to section 5.6. This section describes the harmonics calculation in the following way, that not only the bin directly located at the harmonics shall be taken, but also the spectral bin next, the two spectral bins next to the harmonic bin shall be respected for the harmonics as well. So you have 3 spectral frequency bins which are used for the harmonics calculation. For each harmonic here, you see it for the second here and for the third here. And again, all the rest of the spectral information, which is not used for the harmonics calculation, will afterwards additionally be used for the interharmonics calculation, as you see it here on this illustration here. And finally, the grouping mode 2 is referring to the same standard, IEC 61047, but to section 551. This section describes the harmonics calculation in the following way, that you have to use the entire frequency spectrum and all the frequency bins for the harmonics calculation. So not only the frequency harmonic bin itself and the 2 bins next to each other, but everything included up to half Hertz down the next harmonics and up to half Hertz up to the next harmonics is used for the harmonics calculation. So the entire spectrum is used for the harmonics, and normally there wouldn't be any information left for the interharmonics grouping, but for the sake of completeness, the same interharmonic grouping type as for the grouping type none is chosen here for the interharmonics calculation. So you use everything except the harmonics bin itself and include it into several different interharmonic frequency bands. So much for the different harmonic grouping types.
Okay, and in combination with harmonics, THD and higher frequency groupings are mentioned very often as well. Can you explain us these values?
Yes. Let's start with the THD, THV, and the THC. THD, I think most of you know what the abbreviation means. THD is the abbreviation for the total harmonic distortion. And the total harmonic distortion is calculated on the one hand side for each voltage signal, for the voltage signal of each phase, and on the other hand for the current signal of each phase. And you can specify the maximum harmonic order to upwards which the THD shall be calculated. In this menu here, per default, the THD is calculated for 40 orders, but you can also calculate it for 1000 orders. And the THD information is included in these underlined THD channels here in the voltage section, U2 and U3 underlined THD, and also here in the current section you will find I1 underlined THD for the first current signal, I2 underlined THD for the second current signal, and I3 underline THD for the current of the third phase. In short words, how is the THD calculated? On the numerator side, you sum up the harmonics starting at the second harmonic and sum it up to the maximum specified harmonic order. And on the denominator side, on the denominator side, you will find the first harmonics order. So you calculate the relation between them, calculate the square, sum it up, and calculate the square root, and then you have the THD. And by multiplying it with 100, you will get the THD in percentage. That's on the one hand side the calculation for the voltage. The calculation for the current THD is the same, with the only logical difference that you don't use the voltage harmonics, but the current harmonics here instead on the denominator, on the numerator, and on the denominator side. The THV is the so-called total harmonic voltage. The total harmonic voltage includes everything which is included here on the THD value on the numerator side. So you sum up the orders of the harmonic voltage, starting again at 2 up to the maximum harmonic order. You square it, you sum it up, and you calculate the square root. And the unit behind is voltage. So the total harmonic voltage gives you an indication how much energy is contained in your harmonics instead of and not only in the fundamental frequency. And the same for the THC. It's not a drug, it's the total harmonic current. So you sum up the current harmonics, again starting at the second harmonic order and summing it up to the maximum specified harmonic, and you calculate the square root again, and then you have an indication and a hint how much energy is contained in the harmonics of the signal instead of the fundamental frequency. So much for the additional harmonics, THD, THV, and THZs. So for the more or less for the add-ons of the harmonics. The next parameter which is automatically calculated when the harmonics calculation is enabled is the so-called higher frequency grouping. For the higher frequency grouping, you will get one separate section in the channel list, and with one channel for the higher frequencies of the first voltage signal, for the second and for the third voltage signal, and the same here for the current of phase 1, phase 2, and phase 3. There will be separate higher frequency channels. And at next, I would like to show you how the calculation is done with a brief illustration here. In general, the higher frequency grouping is orientated on so-called fixed frequency bands, and the calculation is done according to IEC 61000-4-7, Appendix B. And this higher frequency grouping is only included as a recommendation there. And the calculation is done from 2 kilohertz to 9 kilohertz. And this illustration here quickly shows and describes the calculation behind. So when we again take the spectral analysis of the individual voltage signal or the individual current signal as the base for the higher frequency grouping, we focus on the spectrum from 2 kilohertz to 9 kilohertz. And we divide the spectrum now in the next step into 200 hertz sections. And we square all the frequency bins here, we sum it up, and we calculate the square root. And then we get all in all 35 higher frequency bins, whereas every single frequency bin represents 200 hertz bandwidth. So the first frequency bin will contain the information from 2 kilohertz to 2.2 kilohertz. The second one, the information from 2.2 kilohertz to 2.4 kilohertz, and so on, up to 9 kilohertz, whereas the last higher frequency bin contains the information from 8.8 kilohertz to 9 kilohertz. And this is done for every single voltage signal of each phase and for every current signal of each phase. And the information is stored into these channels here, which you can find in the channel list. And sorry, one more thing I have to add, nearly forgot it. The calculation is automatically done when the harmonics are enabled, and the calculation is automatically done also when the fundamental frequency is within 10 Hertz to 1000 Hertz. When the fundamental frequency of your system is outside of these boundaries, the calculation is automatically deactivated.
Sorry, my microphone was
anymore.
my microphone, because I had to cough. I'm sorry. We already had one question. The question would be, how do you group for DC components? I think DC components are in harmonics in the 0 bin. Is it true?
Exactly. The DC component of the signal is contained in the very first value, which is written to the harmonics channel and also to the interharmonics channel.
Okay, perfect. That's, I think, the 0 bin, if I'm not mistaken.
Yes, right.
Perfect. Okay. And yeah, so far so good for harmonics, and we are not at the end. Oxygen calculator does even more.
Yeah. Additionally, besides voltage and current harmonics, we also calculate harmonics for power automatically when the harmonics calculation is activated. And you will find harmonics for the active power in the channel list. You will find harmonics for the reactive power in the channel list, and you will find harmonics for the apparent power in the channel list. And the following equations will show you how they are calculated. When we calculate the harmonics power for each individual phase, you use the harmonics of the voltage and multiply it with the harmonics of the current of the respective phase and multiply it with the cosine of the phase shift between voltage and current. And this information will be included, and this information will represent your harmonic power and be available in these channels here in the channel list. Additionally, the so-called THP, the total harmonic power, is calculated, which again, more or less same to the total harmonic voltage, will sum up the active power harmonics starting at the second harmonic power order up to the maximum harmonic power order. And yeah, it's a simple sum. And this value again represents the signal energy contained in your harmonics. The reactive power harmonics are calculated in the way that you again use the voltage harmonics of the respective phase multiplied with the current harmonics of the respective phase and multiplied again with the sign of the phase shift between voltage and current. And last but not least, the apparent power harmonics is just the multiplication of the voltage harmonic of the respective order and the current harmonics of the respective order. And one additional side note, as we already talked about the grouping modes, which are available, the power harmonics are always grouped and calculated according to the grouping mode none. So no matter which grouping mode is selected in your software setting, the power harmonics are always calculated according to the so-called non-grouping type. So only the harmonic bins are taken for the harmonics, for the power harmonics calculation.
Okay. Okay. I think you got one slide more.
Yeah, about the superharmonics. That's the last topic of the harmonics. And then we are finished with the harmonics, promised.
Perfect.
The superharmonics will be calculated when they are enabled by this slide in the software settings. And after having them enabled, you will find a superharmonic section in the voltage group of your channel list and in the current group of your channel list. And They are again calculated for each voltage signal and for each current signal of each phase. And you will find 3 different channels: a min channel, a max channel, and an average channel for each voltage and for each current signal. And the following illustration will hopefully show you clearly in an easy and understandable way which information is included in there. In general, the superharmonics are prescribed as a recommendation in IEC 61000-4-30 Appendix C, and the minimum sample rate for activating the calculation must be 1 megahertz. 1 megahertz minimum sample rate because the superharmonics are calculated and up to 150 kilohertz.
Mhm.
So we need quite a high sample rate for achieving a suitable bandwidth for sampling up to 150 kilohertz. And when we again assume a spectral analysis as the base for the superharmonics calculation, we can deal with a very rough line resolution of the FFT. For example, 2 Hertz line resolution is enough. And then with 2 Hertz line resolution, 150 kilohertz will be the 75th harmonic bin. And the big difference to the conventional harmonics is the following, that not every spectrum is stored into these channels here, but you calculate several spectra successively for a time span of approximately 200 milliseconds, and then you compare the spectra with each other. And of several spectra over a time span of approximately 200 milliseconds, you take a look and check, okay, what's the minimum amplitude for each harmonic bin, what's the maximum amplitude of each harmonic bin, and what's the average amplitude of each harmonic bin. And this information is stored into the min, max, and into the average channel. So you don't get not the exact information, not the exact spectrum is stored into the channels, but only a statistical trend is, and a statistical analysis of the spectrum up to 150 kilohertz is stored to the superharmonics channels to give you an indication what's going on in the frequency domain up to 150 kilohertz.
Okay. Okay, perfect. So these are superharmonics. It's very detailed already. We are very deep in the theory, and that was it for harmonics so far. So let us talk about flicker. Flicker is also very important if you talk about advanced power analysis. So tell us something about flicker.
Yes. In general, what is flicker? Voltage fluctuations in public power grids that lead to visual changes in the light emission of conventional light bulbs is called the flicker. Is called flicker, and the flicker is one or maybe the most important criteria to evaluate the power quality of public power grids and to evaluate the feedback of consumers of loads, of electrical loads into the power grid. And there are 2 different important flicker calculations. The first one is the flicker meter in compliance and in compliance to IEC 61000-4-15. Normally, this flicker analysis is called the voltage flicker emission. And it is done in the following way. When you activate the flicker analysis in the software with the slide here, these channels can be found for each voltage phase in the channel list. All in all, we have 7 individual channels, 7 different channels for each voltage phase, and the following slide will show you which information is contained in these channels. This block diagram here is prescribed in the standard IEC 61000-4-15. And it consists of 5 blocks. The first block has logically the input here, and the input for this block diagram is the voltage signal of each phase. And the first block does a normalization to ensure that the following block diagram here is working independently from the voltage amplitude. So this is a simple normalization. And down here, the so-called D parameters will be output as additional results, which are available here in the channel list. And the following slide will describe which information these D parameters are containing. So I have to ask a little bit for patience for this explanation. And the blocks 2, 3, and 4 simulate the eye brain response of the flicker of the conventional light bulb. And the flicker analysis is prescribed and standardized for 4 different power grid types: for 250 volt 50 Hertz, 120 volt 50 Hertz, 230 volt 60 Hertz, and 120 volt 60 Hertz. And these parameters, the voltage amplitude and the fundamental frequency of the system, are respected here with filters in the third block. And on the output side of the fourth block, the so-called P-inst, the instantaneous flicker sensation, will be output and be available as a signal here in this P-inst channel. And this instantaneous flicker sensation is then fed into the fifth block, where on the one hand side, the short-term flicker severity is output and the long-term flicker severity is output. The short-term flicker severity is calculated according to this formula. This formula already looks pretty confusing, and here you have again some placeholders for even more confusing formulas, which are listed here. So it's quite a big formula. And I will not explain every single parameter, don't worry. I will just explain what these values here, P underline 30, 50, 80, and so on mean. That's a statistical analysis. The P30 includes the instantaneous flicker that's exceeded in 30% of the measurement time. The P50 includes the instantaneous flicker, which is exceeded in 50% of the measurement time, and so on and so on. For 80% of the measurement time, 6%, and so on and so on. And this statistical information is then used to calculate the short-term flicker severity according to this formula. And the aggregation time, so the measurement time of the short-term flicker, can be set here per default according to the IEC standard. The aggregation time is 10 minutes, so the short-term flicker will be updated every 10 minutes. And the short-term flicker severity is in a next step used to calculate the long-term flicker severity according to this formula. And the long-term flicker severity is the cubical average of the short-term flicker severity according to this formula. And the aggregation time of the long-term flicker is normally per default specified in the standard as 120 minutes and can be edited here as well. And when the short-term flicker is 10 minutes, the long-term flicker is 120 minutes. 12 short-term flickers will be used for the calculation of the long-term flicker, for example. And last but not least, this ready channel includes the instant of time when the flicker evaluation is really started. This channel is required because this algorithm here needs some time until it is working and running stable, because it has to bend in. And the ready channel changes from 0 to 1 at the instant of time when this algorithm up here is working stable, and indicate with a change from 0 to 1, the start time of the aggregation time. So this is more or less just an indicator, indicating you when the flicker emission evaluation really has started.
Mhm.
That's
Okay.
the voltage flicker.
Mhm.
And this next slide describes the analysis of the D parameters, which are called the short-term voltage fluctuations. The short-term voltage fluctuations are also prescribed in the IEC 61000-4-15 standard. And for this analysis, the half-periodical RMS values of every voltage channel are calculated internally, and the time-dependent trend is analyzed for the D parameters here in the following way. This trend here indicates the signal trend of the half-periodic RMS values. When the half-periodic RMS values, the average of that, is constant and the change of the average is smaller than plus minus 0.2%, everything is working fine and we don't have a problem. But as soon as the average of the half-periodic RMS value drops below minus 3.3%, this voltage drop will be indicated and stored in the so-called Dmax channel. And additionally, the time, the duration of this voltage drop is stored to the TD channel. And after some time, hopefully, a new steady state will appear and the half-periodic RMS value will be constant again. And the new steady state is reached after the average value of the half-periodic RMS value is within the limit of plus minus 0.2% for at least 1 second again. And that's also the instant of time where the data is updated. And the change from the old steady value to the new steady value is stored to the so-called DC channel. I hope this was not too confusing, but that's the calculation according to the standard. And yeah, that's the information which is stored to these channels here.
Yes. Okay.
And finally, the flicker emission. I have to admit to say that this might be even more confusing than the short-term voltage fluctuations, but I will try to explain it anyway. The flicker emission is the so-called current flicker, and it is calculated and prescribed in the IEC 61400-21 standard. And the channels which are output and filled with data for this calculation can be found in the current section because it is called the current flicker. And for each current signal, you will get all these output values here for each individual current signal of each phase. And I will try to explain you which information there is included in these channels. As the most important base for this calculation, this block diagram is used, which is also prescribed and specified in the standard. The input channel is, or the input signal is the IMT signal, which is the current of each individual and each single phase. And as an output signal, you will get a fixtures voltage. And this fixtures voltage includes the information how the fixtures impedance and fixtures inductance and this constant voltage source will affect the current. And the constant voltage source, the nominal voltage, can be added here and is per default the RMS voltage of your power grid. And the the size, the value of the fixture's impedance and the fixture's inductance can be changed and set by the short circuit apparent power. And here you can find some calculation, some formulas how to determine the correct value. And the output value is the so-called U underline fig, and this is a fixture's voltage determined based on the input current and affected by these three parameters here. And the next slide will show you what is done with this voltages, with this fixtures voltages. Again, here is the output, the fixtures voltage, and per input current you will get 4 different output voltage signals with a phase shift of 30 degree, 50 degree, 70 degree, and 85 degree to your current signal. And these fixtures voltage signals are then again fed into this flicker emission, into this flicker meter, which is described in the second standard. The only difference here is that you don't calculate any key parameters here. And then you will get the instantaneous flicker again for the 30, 50, 70, and 85 degree phase shift, and the short term and the long term flicker values for 30, 50, 70, and 85 degree phase shift. And all this information will then be included here in these individual channels.
Mm-hmm.
So much for the flicker emission.
Perfect. So for those who need those informations and who work with Flickr and harmonics, these informations are going to be worth gold. And thank you for that, Raphael. But let us talk about something that is even for me easier to understand. Let us talk about rolling computation. And I had a lot of customers who need this, who in renewable energy, and I think that's pretty easier to explain, and explains also how oxygen works and calculates the power values as well.
I hope I can explain it in an easy way. To be honest, the rolling computations are no feature of the oxygen advanced power option, but of the oxygen expert power option. But
Okay.
I wanted to include them anyway, and quickly describe the calculation behind. What's the reason for the rolling computations and what's the calculation behind? When we first look on the traditional power analysis and the power calculation, each power parameter is calculated for and updated for each period of the fundamental frequency. The problem hereby is when we cannot detect the fundamental frequency, the power values will not be updated anymore. And when there's some signal processing and testbed behind which needs these values, it cannot work anymore without the power values. And for this reason, the rolling computations were introduced and are described in a technical reference from a German wind energy research institute. And the output rate, or let's start like that. The rolling computations is a statistical RMS calculation. And the output rate of the data is not depending on the fundamental frequency, but the output rate of the data is always 1 kilohertz. So each value is updated for each millisecond. And the statistical window for which the RMS value is calculated is a rolling average or a moving average window with a variable window size, whereas the output rate is still constant in 1 millisecond. The window size of the moving average window can be specified with the nominal frequency here and with the nominal frequency threshold. The nominal frequency can be set to 50 Hertz or to 60 Hertz, and the threshold can be set from 0 to 20%. This setting means the following. When your fundamental frequency is within this specified threshold here and within this specified frequency range, your moving average window size will be exactly one period of your fundamental frequency. So assuming 50 Hertz fundamental frequency, the moving average window size will be 20 milliseconds. Assuming 10% shift to 45 Hertz, your moving average window size will be 22 milliseconds approximately. And when we have 55 Hertz fundamental frequency, your moving average window will have a size of approximately 18 milliseconds. And as long as your fundamental frequency is within this threshold and within these boundaries, everything is fine. And according to the way I just explained. As soon as your fundamental frequency is out of this threshold, out of these boundaries, for example, because the fundamental frequency cannot be determined anymore, then your fallback moving average window block size will be the period of the specified nominal frequency here. So it will be set to a fixed output window again, and you will always have values output at 1 kilohertz output rate and never run out of data to ensure that following signal processing algorithms always get the data and can continue working.
Perfect. So this happens very often at renewable energies. So this is also why it's called the wind energy, whatever appendix or information, the TR3. At the very end, I think that's it for rolling computation, if I'm not mistaken. At the very end, can you tell us what is going to happen to power features in our next release, and when is going to be the next release?
The next release will be by the end of March. And especially for the power customers, we have 3 major features included. At first, we will calculate also automatically the line-to-line harmonics for voltage and current signals. At the moment, you always, when we talk about harmonics, we always mean and imply the neutral line harmonics. But as the line harmonics become more important, again and again, we will also include the line harmonics and the line total harmonic distortion as well, and not only the line neutral total harmonic distortion. And as a long-awaited feature, we will also have a plugin and an option for calculating a DQ analysis automatically in Oxygen with the Oxygen Advanced Power option. For sure, there will be some more very nice and very important new features in 5.5, but these 3 features are, I think, the most important ones for our power customers.
For power customers, exactly. And DQ, if I'm not mistaken, is for motor customers who measure electrical motors. Very important.
Exactly.
Perfect. And since we have still some time left, maybe we could have a short look within Oxygen on how to visualize harmonics, for example.
Yes, as a small practical example for close this webinar, I would just like to show you how you can also visualize your harmonics. And there I want to show you in my opinion, the 2 most convenient ways. The first possibility to visualize the harmonics is to just use the power instrument, which you can drag and drop on the screen by dragging the entire power group on the screen. And I will just increase the size a little bit. And after activating the harmonics, you have this page available here, which shows you the voltage harmonics in green and the voltage interharmonics in orange in the upper graph, and the current harmonics in green and the current interharmonics in orange on the lower graph, changing over time, and the amplitude is in percent. And you have the possibility to swap between the phases by accessing the instrument properties, and also to show the higher frequencies by checking this box here. Then you will see the higher frequency grouping from 2 to 9 kilohertz in percentage amplitude as well. And you also have a possibility to add some cursors for detailed analysis of single harmonics or interharmonics. That's the first possibility. If you're more interested into the absolute amplitude and not only the relative amplitude, I can recommend the array charts instrument for that, which can be found here. Just drag and drop it on the screen again. And then you can assign any harmonic channels, no matter if it's a harmonic voltage or a harmonic current channel, if it's an interharmonic, a superharmonic, or a higher frequency channel. Just select the channel here, and then you have to change the y-axis scaling, and then you can also visualize your superharmonics with an absolute amplitude with this array chart, and for sure any other harmonic signal like the harmonics of the first voltage phase here. Yeah, that's the most that's the two most convenient ways, in my opinion, to visualize the harmonics in oxygen.
Perfect. So of course we can use digital instruments as well, not just visual instruments, but that's even more simple. So you have a predefined way to show values. You have your array chart to do it manually if you want to see something special. Yes, Rafa, thank you so much for your insights and for all this information that you gave us for this still very complex application, and a complex application needs always explanation. We have no questions so far, so all to say from our side is thank you for listening. If you have any further questions, feel free to contact me and my colleagues. Our contact data is available on our homepage or on social media. If you know colleagues who are interested in this application and this information, we are going to be live on Thursday morning and Monday evening, again the same topic. We're going to put also a video on YouTube at the end when all webinars are done, so this information will not be gone. Please stay online for 1 or 2 minutes to give us some answer us some questions, that we know what we can improve with our webinars, and give us some feedback at the end now at the webinar. And yes, all we have to say is thank you for watching, and see you next time. Bye bye.
Thank you for watching. Have a great day. Bye bye.